I'm going to go through this very quickly so I can talk about things that were not in the paper. I used a Q learning agent with a neural network for function approximation, so I didn't have to worry about translating to a discrete state space. The neural network architecture was 400 nodes in a single hidden layer, using leaky ReLU for activation in those nodes, in the hidden nodes, and pseudo Huber loss for the loss function. I'll talk about this one. It's basically to, if your agent were to experience differences in terrain that were just momentary, so you happen to have a trial where your lander would normally land safely, but it just happened to have a mountain there or something, and so it crashes. Normally would cause high error, which would cause large updates to the weights. This loss function is robust to that. It dampens the effect of high loss, which allows you to experience those high loss episodes without moving your weights incorrectly to adapt to the terrain. So it's more generalized and robust. All right, I did 256 batch sizes every 500 steps, played with a whole bunch of things, and that seemed to be a good balance. Epsilon strategy ended up doing a linear epsilon decay over about 1,000 episodes, and I play with these hyperparameters. Okay, we'll get back to these improvements. My agent learned to get an average of 200 reward after about just over 5,000 episodes. Here's my training results. Looks pretty good. There's still a little bit of volatility, so it would be interesting to try to tune the weights a little more. Let's see. Hyperparameters. So I played with every value possible. I cover alpha and epsilon. Low alpha, it was conservative learning curve. Ended up hitting 200 average after 6,000 episodes. So slightly 20% more than the default alpha. High alpha actually never converged, hundreds of thousands of episodes, and it was still unable to reach the 200 average. Epsilon decay. With high epsilon decay, the agent keeps chasing after the optimal Q actions, and the problem with that is it's not able to get enough stochastic experience to learn a generalized behavior, and so your agent experiences high loss areas where it encounters a new state space, loses value, and then has to learn from that to try to recover. And we can see this in the volatility of this learning curve. Low epsilon decay, it experiences a lot of stochasticity and a lot of state spaces before it starts using its Q values. Problem there is it doesn't exploit the Q values as much as it could. So epsilon, the optimal epsilon decay that I found is a good balance between exploiting what it finds in the Q values while still experiencing enough stochastically to learn those edge states, and that so there's a balance there. All right, 1 minute left. So I played with double Q networks, prioritize experience replay, and dueling. So dueling, I didn't get a lot out of. Mainly, I'm guessing due to the fact that the action space is fairly small, and the literature sort of states that this is good in use cases where you have large available actions. Double networks, it was hit or miss. I think the rate at which I update the target network had something to do with it, and I could have played with that more to get more gains, but eventually I just simplified it down to a single network again. And then prioritize experience. My implementation was naive. It didn't use something like a sum tree, so the runtime was long. It did learn quicker, so over less episodes, but it took longer to train, so I abandoned that.